So to give you a bit of motivation, the idea, a bit of background, the idea for an SKA emerged in the early 1990s. Radio astronomy has always been at the frontier of discovery in trying to understand the universe. Radio astronomers are too polite to point this out too often, but it's worth noting that radio astronomy has won more Nobel Prizes than all of the rest of astronomy put together. There have been 4 Nobel Prizes given to radio astronomers. The first was in 1974, given to Ryle for aperture synthesis and for Hewish for discovery by his student of pulsars, as shown here. In 1978, Penzias and Wilson were given the Nobel Prize for their discovery of radio emission from the cosmic microwave background. In 1993, Hulse and Taylor were given the Nobel Prize for using radio emission from pulsars to get the first direct evidence for gravitational waves as predicted by the theory of general relativity. The solid lines here are data, and the points are the data, and the line is not a fit, it's actually an ab initio prediction from general relativity of how the orbit of the binary pulsar would decay. And then most recently, Mather and Smoot won the Nobel Prize in 2006 for detecting anisotropies in the cosmic microwave background. So certainly if you're either a CMB or a pulsar person, then your odds of winning a Nobel Prize are quite good, but certainly radio astronomy has enabled these unique measurements. So clearly radio astronomy is a fruitful area and there's lots more we can do. However, it's been shown in all sorts of fields from medicine to engineering to astronomy that if you want to keep doing new things, then the capability of your instrument, broadly defined, has to keep increasing exponentially. So here is a plot showing you the sensitivity of radio telescopes as a function of time with various instruments going from Grove-Reber's first dish in Chicago through to the VLA, the GMRT, and onto the more recent telescopes here. And you can see that we've done reasonably well at staying on this line for more and more sensitive telescopes. But if we stop here, and it's worth noting that the VLA is still they've got the highest angular resolution of any standard interferometer, and it's now well over 20 years old. We need to keep pushing down here instead of flattening out if we want to keep making discoveries. And so that means that around here in the middle of next decade, we need a telescope which is several orders of magnitude more sensitive than the telescopes that are the workhorse of today, like the VLA. We need something with a total collecting area of about 1 square kilometre, the SKA. So what sort of parameters, what sort of instrumental specifications might such an instrument have? So this will, to do various scientific experiments that I'll describe in a moment, you need a collecting area of approximately 1 square kilometre. But you certainly don't just want to take the VLA or Arecibo or some other large telescope and build more copies of it to get up to 1 square kilometre. Just the sheer processing power and electricity needs of a 1 square kilometre telescope force you to do astronomy in a different way from what you've done before. So it's not just a case of building something bigger than what we've already got, but using 21st century technology. Radio astronomers have never tried to build anything this big before. So for the first time, radio telescope, from the beginning, has had to have been an international development. And at the moment, there are 17 countries, including a large number of countries from Europe, very actively involved in getting funding for and contributing to the design and the science case of the SKA. So it's been an international concept right from the outset. At the moment, there are 2 potential sites for the SKA, and I'll talk about them more in a moment. They're both superb places for radio astronomy, mainly because they're in the middle of nowhere. One of those is near Bulawayo in Western Australia, and the other is in Karoo in the western part of South Africa. A decision between these 2 sites is going to be made at a governmental level, not by scientists, in about 18 months to 2 years. So what will be the basic capabilities of the SKA? Well, at the standard radio frequency observing standard radio frequency of 1.4 gigahertz, it'll have a resolution down to 20 milliarc seconds. But resolution is not everything. If you have very high angular resolution, you might miss smooth large-scale structures. So it'll also have superb sensitivity on all scales, from this very small angular scale right up to scales of many degrees. It'll be a very frequency agile instrument. It'll be able to observe all the way down to 70 megahertz and all the way up to 25 gigahertz. those numbers are not just picked at random. There is specific science which you can only do at those extreme edges of the frequency band, as I'll talk about in a moment. One of the really incredible things about the SKA and about radio telescopes in general is that compared to the most advanced telescopes and other wavelengths, they have a spectacular field of view. At the bare minimum, we're hoping to have a lot more than this, but the absolute minimum, we hope that the field of view of the SKA at 1.4 gigahertz will be 20 square degrees, which makes this sort of instrument not just a point-and-shoot type telescope like the VLA, you pick your object and you stare at it, but an absolutely wondrous machine for doing surveys. You'll be able to cover huge swathes of the sky down to incredible sensitivity extremely rapidly. So just to put that in perspective, here are the fields of view of the most powerful telescope ever built, the Hubble Space Telescope. And for a comparison, the telescope that's about to come online, the Atacama Large Millimeter Array, which is going to be a spectacular instrument for measuring, probing star formation throughout the universe and generally studying the millimeter sky. So those are the fields of view of those two multi-billion-dollar incredible facilities. Here is the field of view at the SKA at a relatively short wavelength of 6 centimeters, that's 5 gigahertz. And at 1.4 gigahertz, at 20 centimeters, this is the field of view of the SKA. So you'll have all the sensitivity and better angular resolution than Hubble, but over a field of view that is millions of times larger. So you can imagine just how many pixels in a single pointing, the amount of data involved in doing even a simple observation with the square kilometre array will totally dwarf anything we've ever had to deal with in any other wavelength before. Not only will you get this enormous field of view with pixels that are only perhaps a fraction of an arc second across, but because all radio telescopes are spectrometers, you'll also get this image in hundreds or thousands or even tens of thousands of channels if you wish. The particular relevance to those that like magnetic fields, it's been insisted on from the start that the SKA have full high-quality polarization capabilities. 25 years later, we're still suffering from the limitations of the very large array because it doesn't have good polarization. There's a huge number of experiments you can't do with it. We hope to correct that mistake from the beginning with the SKA. One of the beautiful things about an interferometer is that interferometer being a telescope spread over multiple dishes is that you don't have to have finished the telescope before you can start using it. You can start making measurements as soon as you've got 2 dishes, and the capabilities of the telescope just grow smoothly as you add more and more dishes into the array. So we expect that construction will start probably in about 2014, but even though it will probably take about a decade to complete the full telescope, as soon as 2 years after the first sod is turned in the ground, we'll already be beginning to make measurements. So this is very different from, say, Hubble or Chandra or Planck. You really can't do any science at all until the spacecraft is actually launched, and that might take 10 years in planning. We can actually enjoy the science and fine-tune our approach, both scientifically in terms of design, while the instrument's still being built. And the total cost in today's dollars will be about €1.5 billion. As I'll spend most of my talk talking about, these particular specifications are very robustly rooted in 5 key science projects, which define what we hope the SKA will do, at least for the first few years. Before I talk about those projects, I'd like to spend a bit of time just telling you about the site. Before I do that, I wanted to just give you an honest impression of what we envisage for the SKA. So here is just an animation showing you what the SKA might look like. I note that this car is driving on the right-hand side of the road, which tells you it's neither South Africa or Australia. But other than that, this gives you a rough idea of what we envisage. So you can see that the SKA will be comprised of a very, very large number of small dishes. Small dishes are cheap. You can stamp them out in a commercial mass production manner. We might need about 40,000 of them to produce a full square kilometre of collecting area. And about half of those small steerable dishes will be concentrated in a central core for maximum surface brightness sensitivity. One of the unique things about the SKA is we won't just have traditional steerable parabolic dishes, but we will also have these tiles, these passive tiles that will essentially stare at the whole sky all the time with no moving parts. So while you're pointing at a particular object of interest, if some gamma ray burst or explosion happens somewhere else, these passive tiles will have picked that up. And these have an incredible field of view, especially good for surveys at low frequencies. Beyond the central core, there'll be other stations, a small number of dishes, spreading out and out in some sort of quasi-spiral pattern, probably for many thousands of kilometres. And that's just the inner, perhaps the inner 30 kilometers or so. So where would you put the SKA? Well, I've already sort of given you the idea of the likely places. This was actually quite a long process that lasted about 5 years. There were many other sites considered, including southwestern United States and China and Argentina and Chile. You want somewhere that obviously needs a lot of open space. There's a lot of 40,000 dishes going on the ground. You need a huge amount of flat land that you can control and that you don't have to worry about cities or roads or other developments getting in the way. On the other hand, you do need infrastructure. If you want to build something that's over €1 billion, you need airports, you need roads, you need power, you need internet. You're going to have a small army of engineers and other staff to run the telescope that have to live somewhere. You don't want to put it in Antarctica or somewhere like Sweden, unfortunately, because in the 21st century approach to multi-wavelength astronomy, you want to be able to see the same swathes of the sky that all the other big telescopes can see. And you also want to see as much of the sky as possible. So that tells you probably want to put it in the southern hemisphere, the same hemisphere where all the big optical telescopes are in Chile and where ALMA will be. But you also don't want it too far south because you want to be able to see more than half the sky. And the most crucial thing is that it has to be an absolutely pristine radio quiet environment. The signals that we're looking for some of the signals that we'll be looking for at the nanojansky level of 10 to the minus 35 watts per square meter per hertz. Even the smallest amounts of terrestrial interference from radio stations, people starting their cars, microwave ovens, mobile phones, be absolutely catastrophic for an incredibly sensitive instrument like the SKA. So you simply cannot put an instrument like this anywhere where there's civilization and radio transmissions. So here's a forte map of the Earth showing you transmissions at a representative frequency within the SKA band of 126 megahertz. And not surprisingly, Europe and most of the US and Asia are not good places to build a radio telescope. If you look at places that meet all these criteria, the international community decided there were really only two options, Peru in South Africa and Western Australia. Every other place either didn't meet the criteria or there were concerns that it might meet the criteria now. There are places in China that are actually quite nice and quiet, but there's so much development and change of urbanization in China that there's no guarantees that in 50 years it will still be quiet. However, I think it's a pretty safe bet that no one will ever be living in the desert of Western Australia. So just to show you one of the two sites, the Australian site. So where is Buladi? Well, here is half of Australia. This is several times larger than Europe, Western Australia, with a population of about 1 million, almost all of whom live in Perth. So this is pretty much completely empty. And Buladi is a small sheep station about here. You fly to Perth, you fly to Geraldton, and it's about a 7-hour drive on dirt road. And well, here's an actual photograph of the site. So it looks not too different from perhaps Mars, if Mars had a few trees. It really is in the middle of nowhere. You can see trees, so it's not desert as you might imagine, but there's really nothing here at all. It never rains, very few animals, pretty much nothing at all except dead flatness. So I talked about the most important criterion being radio quietness. Well, let me show you some actual data taken at various potential sites in Australia. So here is a radio frequency spectrum in the city of Sydney with a population of 4 million, going from 100 megahertz up to 1 gigahertz. And you can see that, not very surprisingly, Sydney, despite being where some of the very first radio astronomy measurements were done in the 1940s and 1950s, is unfortunately no longer a very good place to do radio astronomy. In particular, around 100 megahertz, which turns out to be a crucial frequency for the SKA, it's the frequency at which we expect to detect the epoch of reionization, as I'll talk about in a moment, is completely blasted. 100 megahertz is exactly where the FM band is all over the world. It's absolutely impossible to make any astronomical measurement at 100 megahertz. All you're going to pick up is FM radio. So you can move to somewhere a bit more rural. Australia's most powerful radio telescope at the moment is the Australian Telescope Compact Array, which is just outside Narrabri, which only has a population of 6,000. The Australian Telescope operates up here, which is somewhat more clean. But you can see that even in a small rural town, which is many hours' drive to the next town of comparable size, this is still a bit of a disaster. However, Buladi, our proposed site for the SKA, has a population of 4, and you can see that even in Buladi you cannot get no radio interference at all. But these are all extremely narrow band. If you just simply cut out that channel, you don't get that. Amazingly, the spectrum is pretty much completely empty and unpopulated, and you can make extremely sensitive noise-limited observations even right in the middle of the FM band. And if you go out here and you're driving your car and you turn the dials on the radio, it's just complete static on both AM and FM. So that's something about the site. And the Karoo site looks very similar. It also involves a lot of red dirt and also is incredibly pristine in terms of interference. So let's talk about science. It's a very well-organised team that has been developing the science case for the SKA. The focus of this has been an international science working group, which has about 30 members. For the last 2 years, I was the project scientist. I stepped down at the end of 2007, and Joe Lazio in the US has now taken over that position. We were all locked up in a room in Leiden for about 2 weeks several years ago, and weren't allowed out until we had written a definitive science case, incredibly detailed, about 500 pages, that was published as a special issue of New Astronomy Reviews in 2004. And while that is incredibly diverse and detailed, the focus of that science case are 5 key science projects as follows. I'm going to spend a bit of time talking about each of these in the next few minutes. Probing the dark ages, galaxy evolution, cosmology and dark energy, the origin and evolution of cosmic magnetism, which Rainer Beck and I are the coordinators for, a topic that's dear to the heart of many in this audience, strong field tests of gravity using pulsars and black holes, and the Cradle of Life. And as you can see, and as you'll hear more from me in a moment, these are incredibly diverse topics that tackle a wide range of areas in not just fundamental physics, but also in fundamental astrophysics as well. And even though it's not so much a science project, we also recognise that if you look at those Nobel Prizes that radio astronomers have won, they've all come from things that no one could have predicted. If you look at the proposals for what many of the great radio telescopes of today were going to be used for, they don't mention pulsars or quasars, because pulsars and quasars hadn't been discovered when they were built. And yet that is now the bread and butter of these instruments. Recognising this, I would personally be very surprised if 100 years from now, when my great-grandson or great-granddaughter is giving a review of all the great things the SKA did, I'm very, very surprised that these are the top 5 things that the SKA actually accomplishes. We recognise that it's the things we can't even imagine that are going to be the success stories. So we're trying to keep the telescope as flexible as possible. If we can afford to keep some capability in, even if we don't know why we think we need it, then we try and keep it in. So I'm now going to go through those 5 science projects in turn. And I'll try and give a little bit of background so that those who aren't astronomers can understand what I'm talking about. So one of the last frontiers in astronomy is an era of time lasting perhaps 1 billion years after the beginning of the universe, called the Dark Ages. And the idea is, so here is a complete history of the universe starting at the Big Bang till now. The idea is that there was a Big Bang, and early on in the universe, all of the material in the universe was ionized. The universe was too hot for electrons and protons to combine. But about 300,000 years after the Big Bang, the energy density of the universe dropped by enough that electrons and protons could merge. That was the epoch of recombination. And from then on, the universe was neutral. So you now have an empty universe with no stars, not much light anymore, and just filled with neutral hydrogen gas. A dark and empty place. But eventually, through processes that we don't entirely understand, the first stars and galaxies began to turn on. They were hot and generated ultraviolet photons, and those ultraviolet photons were able to, we think, quite quickly ionize the universe. So right now, if you get outside our galaxy and go into intergalactic space, the universe is 100% ionized. And it's been that way for most of the universe's history. But somewhere around here, the universe made this abrupt transition from neutral to ionized, and for somewhat confusing reasons, it's called the epoch of reionization, because it was ionized back here. So around 1 billion years after the Big Bang, somehow the universe ionized. And if we could see that process happen, we could actually understand whether the structure of the universe formed through top down or bottom up. We could understand what role dark matter played. We could understand the properties of the first stars and galaxies and black holes. So one of the last frontiers in cosmology, we can see all of this stuff very well, and we can see this surface here. This is what those Nobel Prizes are won for. We can never see beyond that surface because it's completely opaque, but there is this period here where we currently have no information whatsoever. the dark energies. But one of the exciting things is that neutral hydrogen emits a emission line at a radio frequency of 1.4 gigahertz, a hyperfine transition, the 21 centimeter line, or H1. And so all of this stuff here was either, depending on what phase, was either emitting or absorbing in this H1 line. Now, because the universe is expanding, that emission is redshifted down to a frequency probably of about 100, 120 megahertz. But if you have a telescope that has enough sensitivity, if you find somehow a way to build a telescope away from the FM band, which sits exactly between 120 megahertz, then you could potentially see redshifted emission from the first structures in the universe being formed. So one of the key goals of the SKA is to basically go to high enough redshifts that we can see that H1, and then as you tune the telescope higher and higher in frequency, you'll actually see that material evaporate. And the rate at which it evaporates and the morphologies that you see will be a direct map of structural formation in the universe. So I can't show you any data, obviously, but here's a simulation from Nick and Aidan showing you this is the universe moving forward time, and you can see these bubbles of ionized gas turning on, and then there is almost a phase transition where almost instantly the whole universe suddenly, it's about to happen now, becomes ionized. So that's what we hope to see with the SKA. Maybe not something as beautiful as this simulation, but we will certainly hope to see both in frequency space and on the sky the universe evaporating before our eyes. One of the other great problems in astronomy at the moment is that we don't know what the universe is made of. The fact that we can put this plot up here at all is pretty incredible and basically lay out the ingredients of the universe. The stuff that we're made of is 0.03% of the universe. Neutrinos perhaps 10 times more than that. Stars a bit more. Free floating gas about 4%. And the rest of the universe is dark matter, which is somewhat passé these days, but dark energy, some mysterious field or force that makes up 65 to 70% of the universe. And we have no idea what this stuff is. We don't know its equation of state. We don't know how it's evolved over time. But at the moment, it's beginning to dominate the evolution of the universe. As one of my colleagues, Bob Kirshner, likes to say, he said the universe is like Los Angeles. It's about 1/3 substance and 2/3 energy. So the SKA will be one of 3 or 4 major experiments in the 21st century, which together will provide critical complementary information that will allow us to understand dark energy. And the SKA aims to do this through what's quite a simple but rather clever idea. And that's that all galaxies that we know of have hydrogen gas in them. And so if you build a powerful enough telescope, then if you tune your telescope to that hydrogen emission line of 21 centimeters, 1.4 gigahertz, then in principle you can detect a galaxy anywhere in the universe, simply not by seeing the stars in that galaxy, but by picking up the hydrogen line from the gas. So that's interesting in its own right, because you can use it to study galaxies and their gas content and their rotation curves. But you can also simply use that you can exploit that to use galaxies as markers throughout the universe. So you simply do a completely blind survey of the sky with the SKA. You survey huge swathes of the sky at all possible frequencies, and you pick up, just like beads floating in water, H1 from galaxies all over the place. Now the galaxies are not randomly distributed, but they'll be very subtly clustered in a way that is an imprint of the first structures in the universe after the universe began to cool. And that turns out to be a standard ruler. There was a certain clump size that galaxies congealed out of very early on in the universe. And that clump size has been frozen into the structure of the universe ever since. So the universe has a beautiful built-in standard ruler. If you can measure the distribution of galaxies anywhere in the universe, you can measure their clumping and you can use that as a standard ruler. Now, one thing that dark energy does is it causes the universe to accelerate and to expand more rapidly. So if you could simply apply the standard ruler at all different distances going back in time and seeing how this ruler changes size, you have a beautiful measurement as a function of time of how dark energy has evolved. And that very nicely gives you the equation of state of dark energy, which allows you to help, hopefully, it will let us figure out just what it is of the hundreds of different models at the moment. And you can only do this with the SKA. The measurements that have been done on dark energy right now go out to rather low redshifts. But with the SKA, this is a matter power spectrum of the universe. This is the strength of clustering in galaxies versus 1 over the scale size. And here is what you might find for relatively nearby galaxies. So these ripples or wiggles represent the imprint of the structure formed at the beginning of the universe in galaxies now. And as you move backwards in time, these ripples change in their positions to the left and the right, which indicates that the standard ruler is being shrunk or stretched by the effect of dark energy. And only with the SKA using H1 you can actually push back over billions of years, over more than half the universe's age, to see how the universe has been stretched by dark energy over time. At the same time, that's fundamental physics, but at the same time these galaxies all contain actual physical information. If you detect H1 in a galaxy, then you know how much mass is in that galaxy. And one of the big questions that cosmologists are wrestling with at the moment is, how do galaxies assemble? How do they evolve? Where does their gas go? If you take the star formation rate at any point in the universe and take the amount of gas that we have in the universe at the same time, then that rate of star formation should be able to use up all that gas within less than 1 billion years. So it's a bit of a puzzle as to why we're actually here and why stars are still being formed. To answer that question, we really need to be able to map out the actual gas content of the universe as a function of time. So here are some very brave attempts to do this. So this is redshift starting at the present and going back in time to about 10 or 12 billion years ago. And this is how much gas there is in the universe as a function of time. And you can see that the errors on these measurements, which are very difficult measurements to make, are just so large that it's hard to say anything. You could argue that the gas content of the universe has not evolved at all in time. You could argue that it's falling away. You could also probably argue that it might be increasing or have some more complicated measurement. With the SKA, by just simply detecting all of these billions of galaxies, we'll be able to make incredibly precise measurements of how much gas there was in the universe, and whether it was distributed in big objects or small objects or merging objects or something in between, at every very narrow redshift slices going back billions of years. So this will give us a superb template showing us how galaxies have assembled or broken apart over time, and that can be directly mapped to theories of star formation and galaxy evolution. The key science project that's dearest to my heart and to many of yours is the origin and evolution of cosmic magnetism. And this beautiful image from Andrew and Rana really sums things up. Here is a very pretty galaxy seen in the optical, and overlaid on it as vectors are the magnetic field lines of this galaxy. So galaxies are violent, turbulent places. Galaxies are always smashing into other galaxies. There are explosions going off. This galaxy is being distorted by this other galaxy over here. And yet somehow, despite this complicated interaction, this galaxy has generated a spectacularly coherent magnetic field that's wonderfully ordered and surprisingly strong, which spreads over many tens of thousands of light years. So one of the big questions that we've spent this whole week discussing is, how do galaxies do this? How does the whole universe do this? We think this magnetic field lines, of course, have to close, so we think perhaps these field lines go off somewhere and perhaps join up to other nearby galaxies. The whole universe is magnetized. We don't know where that magnetism came from. We don't know how, what processes have organized it into such incredible coherence. And we don't know what has maintained that magnetism and stopped it decaying away. So the SK can really make a huge advance at understanding this. Couldn't find any Swedish Faraday rotation slides, my apologies. We use a simple effect that Michael Faraday demonstrated over 100 years ago, and that's that if you have a birefringent medium and a magnetic field, well, if you have a birefringent medium, it will rotate the plane of polarization of the light. So you have light that's polarized, and when it comes out of this material, it emerges with a different angle. It turns out that ionized gas and magnetic fields are birefringent to radio waves. So if you have any random radio source, doesn't matter what it is, if it's polarized, then any invisible foreground slab of magnetic material will Faraday rotate that light. And we can use that to probe magnetic fields across the entire universe. Radio waves are not absorbed by just about anything. Optical light is very heavily absorbed. X-rays are absorbed. We can see radio waves all the way back to the edge of the universe, hence our ability to see the cosmic microwave background. So anything that's polarized, the CMB, the cosmic microwave background, is polarized. With telescopes like the SK, we'll even be able to measure Faraday rotation of the cosmic microwave background and have an incredible plumb line going from 300,000 years after the Big Bang to now, measuring the magnetic field along that line of sight. So what could you do with this? Well, Ryan and I envisaged something we call the rotation measure grid. And the idea is that you simply survey the entire sky looking for random background sources. There'll probably be supermassive black holes or active galaxies, but it really doesn't matter. All that matters is that they're distant and they're polarized. If you do this over the whole sky, you get about 10 million background sources. So here's a simulation of what we'll get with the SKA. This supposes that we only have a 1 square degree SKA. If you recall, I said the minimum field of view that we can accept is about 20 square degrees. I'm not showing you 20 square degrees just simply because my laptop couldn't handle the number of pixels to generate that simulation. So this is a 1/20th of a 1/20th scaled down version. And this is what an image of the sky you'll get after 1 hour. Now this actually doesn't look that different from a typical image we can get now. The key point is that this is not an image of the intensity from the radio sky. This is an image of the linear polarization. If I showed you the total intensity, this would just be filled with so many sources you couldn't see between them. But these are just the polarized sources. And every single one of these sources, you can measure this Faraday rotation effect and infer the magnetic field strength of anything you want to stick in front of it. So you might want to take your favorite object. That might be, we're just zooming in here. Take your favorite object, say a galaxy, and you have, just for one galaxy maybe, in only a short 1 hour observation, perhaps 20 different plumb lines through that galaxy to map out its 3D magnetic field. Multiply this by tens of thousands of galaxies at all imaginable orientations and inclinations, and you have an absolutely incredible database for studying how magnetism originates in galaxies. See, Chris is looking rather excited about this prospect. It's a very difficult measurement to do right now. For a typical galaxy, you might get one object behind it, but you'll routinely have 20 or 50 or 100 rotation measures behind every object. If you just forget actual individual galaxies and ask, well, what is the magnetic field of the entire universe? The stuff between the galaxies is also magnetic, but probably much weaker, maybe at the strength of a nanogauss compared to a microgauss inside galaxies. Well, it turns out that we can do that too. Here's a simulation showing you that if you simply measure lots and lots of different background rotation measures, and you then plot the strength of the rotation measure against redshift, against distance, then just by the sheer weight of your statistics, the very, very weak magnetic signal of the intergalactic medium will be teased out of your data. So this shows you, if you simply plot the mean rotation measure versus redshift, from redshift of 0 to 2, you get this very slight increase, and that is enough to both map out the strength of the magnetic field in the intergalactic medium, and also to characterize its geometry and its length scale. So that field has not been detected, it's been inferred indirectly, but if we actually measure it, we'll have a huge step forward in understanding how the overall universe was magnetized. And then finally with the SKA, we actually expect that the cosmic web itself, the diffuse filaments of dark matter and gas that connect all the galaxies into large-scale structure, we expect that cosmological shocks have actually accelerated particles in that intergalactic medium, and that the intergalactic medium itself is a source of a very weak network of synchrotron emission. So Faraday rotation is in some sense a propagation effect. It's an indirect measurement of magnetic fields. We could hope to actually directly observe the magnetized cosmic web by seeing very low surface brightness synchrotron emission from the SKA. Moving on to gravity, of course, we'll deal with cosmology and magnetism. Well, of course, the other big unanswered problem in physics is what is gravity? What is the best theory of gravity? General relativity has stood up pretty well for almost 100 years, but we've never tested general relativity in the strong field limit. All the spectacular tests that we've done, both in the solar system and using pulsars, have all been weak field tests. The idea is to try and push general relativity as hard as you can and see if it breaks. And we again can do that with the SKA. The first thing we want to do is to directly confirm one of the predictions of general relativity, which is that accelerating bodies generate gravitational radiation. Now, Hulse and Taylor won the Nobel Prize for indirect evidence of that, because they saw a binary pulsar orbit decay as a function of time in accordance with the predictions of gravitational wave emission from general relativity. But that is not a direct measurement. What you really want to do is actually directly measure the stretching of space as a gravity wave propagates through you. And there's a number of experiments to do that, such as LIGO and LISA, that are either running or being developed. But a completely independent and somewhat cheaper way of doing this is with pulsars. Pulsars are the hypothetical perfect clocks that you learn about in your relativity classes as an undergraduate. And by having an ensemble of pulsars throughout the universe, let me show that video again, you have tens of thousands of pulsars, all perfect clocks spread throughout the galaxy. Then as a gravitational wave propagates through the Earth, some lines of sight to pulsars will be compressed, and others will be stretched because the gravitational wave is dominated by a quadrupole moment. And that means that the arrival times of these perfect clocks will all be distorted across the sky in a very characteristic way that can't be explained by any other systematic effect. There's all sorts of nasty systematics in measuring the exact arrival times of pulses on Earth associated with continental drift and solar system ephemeris and all sorts of other things. But the characteristic quadrupole moment of a gravitational wave can't be mimicked by any other effect. So if we can continuously monitor hundreds of these perfect clocks all over the sky, and some of the pulses on these sides of the sky start arriving early, and the ones up here start arriving late. We know that a gravitational wave with a wavelength of several years is actually sweeping across the Earth, and we will have directly measured, not indirectly, but directly seen the compression and stretching of space-time by a gravitational wave. So that would be a spectacular confirmation of general relativity, and it would also allow us to do experiments, because these gravitational waves that we see passing through the Earth, we believe, would actually be produced by the merging of distant supermassive black holes, so we can actually use this effect to map out the structural formation from merging galaxies throughout the universe. One of the other things we hope to do is that we believe, we're pretty sure, that there are many hundreds of neutron stars swarming at the galactic center. The center of our galaxy has a giant black hole, which weighs many millions of solar masses. There's a lot of hot stars there that are going supernova in that area, and they form pulsars which then orbit the central black hole. Now, the problem with detecting a pulsar around a black hole at the center of our galaxy is it's a very messy region with horrific scattering and absorption. And so you need a very sensitive telescope that can go to high frequencies to see pulsars in orbit around the central black hole. But if you could do this, if you could detect pulsars around the black hole at the center of our galaxy, there's all sorts of subtle effects associated with strong gravity that you should be able to measure in their timing residuals. And in particular, you could make a direct and extremely precise measurement of the spin of a black hole and directly test that against general relativity. And finally, we expect that perhaps 1 in a few thousand pulsars is in orbit around a solar mass black hole. We haven't found any yet, but if we can increase the number of pulsars in the galaxy by a factor of 10, then we should be able to find at least one black hole pulsar binary. And as the pulsar goes through a periastron around the black hole, there should be all sorts of additional effects associated with frame dragging and other things that will allow us to do new tests of general relativity that we have not done before. So pulsars, simply as perfect, accurate clocks, allow us to do a huge amount of precision experiments on gravity. And the last key science project for the SKA is the Cradle of Life. The idea here is that the SKA is uniquely placed to understand how life emerges in the universe. Here is where we think it all happens, in dark molecular clouds. There's not a hole in the sky here, but this is simply a foreground cloud that's absorbing the light from behind it. And we know that these clouds are mainly hydrogen, molecular hydrogen, but also full of more complicated molecules like carbon monoxide and ethanol and so on. But one of the incredible recent developments that has been made possible by the Green Bank telescope, which is an extremely sensitive telescope in the US, is the detection of extremely complicated biological molecules. Some of the molecules that have now been detected in molecular clouds include acetaldehyde, I'm not sure I pronounce that, acetaldehyde, acetamide, cyclopropanone, and propanol, and there's also been a disputed claim of an amino acid in a molecular cloud as well. So, however they got there, some of the building blocks of life seem to be sitting out there in interstellar space. Astrochemistry and astrobiology is very much now focused on understanding what's generating these molecules, how they're distributed, and are there even more complicated molecules with weaker signals hidden in these molecular clouds. And as you can see, these are all frequencies. These complicated molecules have relatively low energy transitions, which are all in the frequency band of the SKA. We hope that instead, these experiments are currently right at the threshold of sensitivity. With the SKA, we hope to make spectacular mapping of all sorts of complicated biological molecules in molecular clouds. Of course, not enough just to have the biological molecules, you need a planet to put them on. The SKA is uniquely placed to understand how Earth-like planets form. Telescopes like ALMA are going to be spectacular for studying the formation of planets. But if you want to see the Earth form, then you need to have an angular resolution such that you can see the distance from a star to the distance of the Earth. That's 1 astronomical unit, about 150 million kilometers. It turns out the SKA will be the only telescope in the right frequency band that will have 1 astronomical unit angular resolution at the distance to nearby star-forming regions. Telescopes like ALMA will be spectacular for seeing how planets will form around their stars at the distance of, say, Jupiter. But they'll have nothing to say about planets 1 astronomical unit from their host star. So this is not, we're not likely to get images of this sort of quality from the SKA, But the point I'm trying to make here is that protoplanets clear out gaps in their orbits. You probably won't be able to detect the planets themselves, but you'll be able to quite easily image gaps in protoplanetary disks associated with planets forming. And one of the exciting things is if you have an Earth-like planet that's 1 astronomical unit from its parent star, then it obviously will take about 1 year to orbit. And that will mean that you can actually watch these gaps evolve in real time. You can come back 6 months later and you'll be able to map out resonances and clearing and interactions between multiple planets and so on. We'll get our first concrete measurements of how Earth-like planets are assembled. And one other thing I haven't put on here is the third step of the Cradle of Life is, well, the molecules in the planets become moot if you can actually talk to somebody. We will have the sensitivity with the SKA to pick up leakage radiation, TV and mobile phones and aircraft radar from other intelligent civilizations out to distances of many hundreds of light years. Although there's been a huge amount of effort over the last few decades in searching for intelligent signals from other civilizations, it's always going to be a long shot because we just don't have the sensitivity to detect something unless it's being beamed straight at us. If someone is signaling to us, we can detect it. But if they either don't know we're there or that they're trying to avoid us, then we just don't have the sensitivity to detect that. If there is a civilization out there and it has not particularly well-shielded radio transmissions, then with the SKA, we'll be able to detect those signals out to a reasonable distance. And those experiments can beautifully and harmlessly piggyback on all the other science that we'll be doing. So having gone through all the science that we hope we'll do, I just want to return to this idea that we really don't know what the SKA will do. As I said, perhaps this is what those things will be, what the SKA does in its first 5 years. And it's not like after 5 years we'll be saying, well, now what? But we'll be drowning in completely unexpected discoveries simply because we'll have a sensitivity 100 times better than anything we have today. So this concept has actually been around for a long time. I don't think Hamlet was an astronomer, but he certainly understood the point. He said there are more things in heaven and earth, Horatio, than are dreamt of in your philosophy. Obviously, Horatio was focused on key science projects and not thinking beyond to the unexpected things that telescopes can discover. In the 20th century, J.B.S. Haldane put it that the universe is not only queerer than we suppose, but queerer than we can suppose. And I'd like to round out this excursion with one of the great philosophers of the 21st century, Donald Rumsfeld, who really captured in saying, as we know there are known knowns, there are things we know we know. We also know there are known unknowns, that is to say we know there are some things we do not know. But as every astronomer knows, there are also unknown unknowns, the ones we don't know, we don't know. Although you can never write a funding proposal for unknown unknowns, those are of course the things that as scientists we very much hope to discover with an instrument like the SKA. So if I can just speculate to go through Mr. Rumsfeld's known knowns and so on. So if you think about known knowns, well, things that we know exist, we just haven't found them yet. To see neutral hydrogen in galaxies out to redshifts of 2, going back several billion years. We can see neutral hydrogen in nearby galaxies, and we know there are galaxies that are more distant. We know they have hydrogen in them, we just can't detect it yet. Those will be easy pickings for the SKA. We know there are pulsars throughout the galaxy and in globular clusters, and as I've described to you, we can do a lot of fundamental physics tests if we find more of them. You can never find too many pulsars, and if we have a bigger telescope, we'll be able to find more of them. So there are some known knowns. There are other known knowns, things that we don't even have any examples of yet, but that should be there. We hope to be able to study Earth-like protoplanets. And we know the universe was neutral early on, and we know that it's ionized now, so somewhere between the beginning and now it has to have reionized, and we should be able to detect that. So those are the known knowns. What about the known unknowns? Well, gamma ray bursts are these huge cataclysmic explosions that give off prompt emission in X-rays and gamma rays. And we know that eventually, many days afterwards, you see these slowly fading radio afterglows probing the explosion slamming into the surroundings. But if we want to actually get to the heart of the physics of these mysterious distant explosions, then we really need, for a number of reasons, radio emission, because it acts as a calorimeter on the total energy of the explosion. If we could just be looking at a gamma ray burst at the instant it went off, we would hope to see a bright flash of radio emission from it, which would be an incredible insight into what's actually happening. But because radio telescopes have such small fields of view right now, we're just never looking at the right place at the right time. But with a telescope with a 20 square degree field of view, you could quite simply design experiments to pick up gamma ray bursts and see the radio flash from them in real time. And as I discussed, extraterrestrial intelligence, very much a known unknown. We don't know what's out there, but we know what we think we should look for, and we know how to do it. And finally, there are the unknown unknowns. Obviously, I don't know what these are, but you can speculate. There might be stars that are made of strange quark matter. There might be black holes without event horizons. There might be magnetic monopoles. These are all things that, if they exist, then we should be able to detect them with SKA. And of course, what we actually detect, well, who knows? So just to show you that this isn't sort of speculation, I should say that as project scientist, when I came on board, I was not excited by the exploration of the unknown. I was very much of the opinion that everything that's worth discovering we already know about, and we just have to understand it better. But some of my colleagues told me I was talking like an old man, and I've now changed my mind, because just over the last few years, I'm just going to give you an example of one area in which there's been a whole flood of new results. And that's the area of transients, the time domain. We're used to studying the spectra of objects, and we're used to studying their positions, and we're used to studying their polarization. But the thing that most people don't pay much attention to is the fact that objects change with time. There's certainly many people who work in this area, but particularly in radio astronomy, it has not been a big area of study. The sky is generally assumed erroneously to be unchanging. But let me just give you an example of, just in the last couple of years, some of the brand new types of radio transients that we now know exist. Probably my favourite are the RATs, the rotating radio transients. A RAT is, we now think, at first we had no idea what they were, but we now think they are normal pulsars. But instead of a pulsar that gives off a beat of radio emission every rotation, these RATs just decide to only do it every few days. So you'll get one pulse from a RAT, and then absolutely nothing for hours, days, weeks, and then another one. Then you wait a few more weeks and you get another one. And one of the beautiful things about radio astronomy is you can measure the arrival times of these pulses so precisely that even if you have 5 or 6 bursts spread over a month, you can actually work out the lowest common denominator the lowest common denominator of their separations, and still calculate a rotation period to 5 or 10 decimal places, even with only a handful of pulses. But clearly this tells you that there are perhaps 10 times more pulsars out there than we thought. It's just that most of them just don't choose to give off emission most of the time. So this is something which originally was quite mysterious, but turns out just to be merely interesting. But there's more. There's another pulsar that I termed the winker. So this is a plot of time, and this is a plot of the spin frequency of the pulsar versus time. Now all pulsars are slowing down, so no surprises to find out that the pulsar is spinning faster here than it is here. But these points show when the pulsar was detected. During these periods, despite very sensitive observations, the pulsar was not detected. So this pulsar is on for several months, then it switches off, switches on again, and it switches off. And once more, if you look carefully, if you join up these dots, you can see the slope of this line is not the same as the mean slope. The pulsar actually spins down faster when it's on, and then it slows down again when it's off. So it's like having an electric fan and turning it on and letting it slow down and turning it back on again. The difference between this slope and the mean slope gives you a direct measurement of magnetospheric current around neutron stars. So this is yet another pulsar, and this is interesting too, but there's things that aren't neutron star. There's an object that I've called the burper. No one really likes this one, but this name started catching on. This is an object, we have no idea what it is. It's near the galactic center. Every 70 minutes, these are 4 different observations, it gives us a huge burp going up to a flux of many Janskis, which is incredibly bright, for about 11 minutes, and then it turns off again for 60 minutes. If you come back a few weeks later, it's gone completely. If you come back a few years later, it's back on again. We have absolutely no idea what this object is. But it burps every now and then for 10 minutes every 70 minutes. And then the most recent one, which just was published a few months ago in Science, is what Sri Kulkarni is called the Sparker. And this was a single pulse. It was 30 Janskis, which is unbelievably bright, detected with Parkes towards a small Magellanic Cloud. So here is the actual profile of this single burst. And you might say, well, maybe this is just another RAT, or one pulse from a pulsar. But the kicker is that this is a plot of this pulse versus time and in frequency. And you can see that the pulse arrived almost half a second later at 1.2 gigahertz than it did at 1.5 gigahertz. And this parabolic slope here is due to dispersion in interstellar gas. Ionized gas, in ionized gas, it's well known that high-frequency radio waves travel faster than low-frequency radio waves. And the time delay tells you how much gas this is propagated through. The dispersion measure was about 300 parsecs per cubic centimetre, which is absolutely insane. This object cannot be in the Small Magellanic Cloud. It has to be many billions of light years away. We do not know what this was. It's certainly not a pulsar. Way too bright. But this 30 Jansky pulse was generated at cosmological distances and then slammed into the radio telescope and was never repeated. We have no idea what this object was, but you can work out, based on the statistics of one event in their survey, that there are 400 of these going off somewhere in the sky every day. So we have no idea what these sparkers are. They may be gamma ray. They may be that prompt emission from gamma ray bursts that I talked about. They could be merging black holes. They could be cosmological defects. We have no idea what this is. But there's 400 30 Jansky bursts going off at cosmological distances all over the sky every day. And if we want to understand these objects, then we're going to need something with the survey capabilities of the SKA. So, fortunately, the SKA isn't all about talking how great the future is and just waiting till the year 2015 or 2020 when we finally get something. As I said at the start of my talk, the exciting thing is that there is a huge amount of money flowing into this project. Several hundred million euros are already being committed and more to come. I think it was the largest grant awarded in the European Union's FP7. And so things are being built. There are many SKA prototypes and pathfinders that are already beginning to take data. There's perhaps about a dozen altogether, but I'm just going to run through a few of them. Probably the one that's most advanced and is already taking data is a Dutch and German and British and Polish experiment, LOFAR, the Low Frequency Array. It's running right now. It consists of these passive antennae that are designed for looking at very low frequencies, and the goal of LOFAR is to detect the epoch of reionization, this low frequency redshift at H1 experiment. This telescope is built exactly where you don't want to build a sensitive radio telescope, in the middle of Europe. So trying to observe very weak signals in the FM band from Europe is very challenging. But even if scientifically they are not able to detect the signal, the technology that they are developing and the data processing are absolutely crucial to the eventual success of the SKA. A very different telescope is this one, the Allen Telescope Array, which is focusing on the idea that if you can build lots of cheap small dishes, you can accumulate large amounts of collecting area very quickly. This telescope is in Northern California, and these dishes are only 6 meters across. They're commercially produced. They're bought en masse and trucked in. They can be assembled in less than a day. And at the moment, there are 42 of these dishes. Eventually, there'll be over 300. And one of the main goals for the Allen Telescope Array is to search for extraterrestrial intelligence, but astronomy can seamlessly piggyback on that at the same time. In Australia, we are refurbishing a rather old telescope Malonglo and reincarnating it as SCAMP, the SKA Malonglo prototype, which will have 18,000 of square meters of collecting area and full polarization. And the idea is to make a map of the Faraday rotation from the entire sky, moving towards that later this year. Back to Europe, there's a telescope called Embrace, which is, again, one of these passive tiles designed to make very wide-field area surveys of redshifted hydrogen from distant galaxies. And then the two big prototypes, the $100 million prototypes that are being developed, one in South Africa called MeerKAT, KAT, the Karoo Array Telescope. And I think Meer is Dutch for big or something. This is going to be an array of small dishes that will have a number of science applications, including pulsars. And the Australian version of that is something called ASCAP, the Australian SKA prototype. And this telescope, which will be built in the next few years, has a focal plane array, giving it perhaps 100 square degree field of view. You'll be able to survey the entire sky every night in radio waves. And the goal here is to map out H1 from distant galaxies. So you can see these ones are photographs, these ones are still artist impressions, but there is steel and electronics being put on the ground at the SK sites. There's a huge amount of money from both the host countries and other countries going into this. This incredibly ambitious project is actually starting to happen. So to conclude, I hope I've convinced you that the SKA is going to be an incredibly flexible and powerful instrument. It will address not one but many fundamental unsolved problems in physics, in astrophysics and cosmology. Here's an animation of a known system. This is a double pulsar, two pulsars that are in orbit around each other, that is already doing amazing tests of general relativity. If we can find a factor of 100 more pulsars, you can imagine some of the spectacular systems we'll be able to use to probe the nature of gravity. The SKA, as radio astronomy always has, will make measurements that you simply cannot make in any other waveband. If you want to measure magnetism, well then you just can't do it in the optical and the X-rays because there is no probe of magnetism. Through unique measurements like synchrotron emission and Faraday rotation, you have a unique view of the universe. Similarly, this ubiquitous 21 centimeter hydrogen line, if you want to measure gas from the beginning of the universe to now, the only way you can do it is in a hydrogen And of course we need to sell the SKA both to our colleagues, to funding agencies, and to the general public. This is not some abstruse experiment where we don't have to explain to people why the Higgs particle is interesting. We can sell this simply on the excitement of the prospects of discovery. We are looking for the most basic questions in the universe. Where do we come from? How did galaxies form? And is there anyone else out there like us? And the bottom line is, despite all these carefully crafted specifications and science surveys and goals, the real exciting and most exciting reality of the SKA is that it will take us places that we currently can't even imagine. Thanks very much.
Thank you, Brian. Thank you, Brian. Questions, please. Yes.
Can you say something about the main technical and political problems with the SKA?
Well, there are
the SKAs.
So you'll get different views from different people. No one claims that we know how to do this right now. I think, in my opinion, the biggest technical challenge will be computation. You have 40,000 dishes, and in real time you have to multiply the signals from every dish with every other dish. So that, if you appeal to Moore's law, which over a 10-year timescale is quite reasonable, we will be able to do it, but the power requirements will be of the order of a gigawatt. So you'll need your own nuclear reactor to power the correlator to analyze all this data. So we are going to need big leaps forward in computation. I think one of the most exciting prospects right now is computer games, in that graphics processor units basically take lots of complicated different things happening at once and combine them. Some of the big computer game companies are now releasing their graphics processor units to astronomers with the code, and we're beginning to write algorithms which are 100 or 1,000 times faster than what we've been able to do before, without the consequent increase in power. So we're at least hopeful that computer gaming might be the way to actually deal with these incredibly complicated computational problems. Politically, I mean, I don't think it's hard to comment. Obviously, there's a decision on a site, and both countries that are pumping money into it now might not be so enthusiastic if the telescope is going to go somewhere else. But from my own viewpoint, what I can see is that the negotiations have actually been very harmonious, given the different timescales. The European Union has this framework program to deliver large amounts of infrastructure, while the US has budget problems and is saying we can't give any money at all right now. But I think that the people at the higher levels are actually being remarkably collegial about trying to link all the money together. We're at about the 300 million euro stage now, and people are still talking to each other. So I regard that as a pretty good sign.
Other questions? This clumpiness, which, or the business with the ruler that you explained in the beginning, I didn't quite follow this. I wanted to know why it was actually independent of time, through cosmological time. Is that
why it's independent? No, it's dependent. That's what you're trying to measure. So this is what you get nearby. This is a very low redshift. The black is real data from the 2DF galaxy survey. This is the matter power spectrum of the universe. These ripples are the real structure of the universe now. But the hope is that there's very slight shifts here. Yeah. Maybe this isn't the best plot, but these are shifting with time in a way that is in line with a particular model for how dark energy would evolve in time. Yeah. If these peaks don't evolve, then that tells you something very disturbing about what was made so far. Yes. And one thing I didn't mention is that you can at the same time use these data to measure the mass of a neutrino, because the way in which structure has formed is very slightly depends on the mass of neutrinos. So if you can measure the shape of the spectrum with sufficient precision, you can actually measure neutrino masses better than any particle experiment on Earth.
Yes, Amber, please.
Right, so there are these key scientific areas. Do I understand correctly that they have been identified and formulated just to help to design the telescope? So what will be the role of people who are involved in formulating this key sequence area and allocating the observing time? How it will be allocated?
Right, so parallel to the science working group is a whole separate working group for the operations working group who have to make these difficult decisions. Nothing has been decided yet, but the expectation is the SK will not work like any telescope we're used to dealing with now. There might not be a time assignment committee. There will be teams set up to do surveys, and that data will be carried out and then made public. So a bit like the Sloan survey now. in that there are these teams that you can join if you can bring something to it, and you work on a particular project, and then those data are made available. And what you see from Sloan is that there's all sorts of science that people in Sloan have absolutely no interest in that have been enabled by the public release of those data. So I would imagine, at least initially, the science time will be allocated amongst these projects, with perhaps a small amount of time available for individual ideas and projects. But given that each of these projects, detecting 1 billion galaxies for dark energy will take many years, even with 20% of the telescope. So you really have to start doing these big surveys right away. I think one of the mistakes that we've repeatedly made with telescopes like the VLA is you do lots of little postage stamp observations for 20 years, and then only then you start doing surveys like the NVSS that enable fundamentally new science. So given the field of view of the SKA, we hope to learn from that and start doing the big surveys straight away. Unfortunately, that means that astronomy will change. We'll be more like particle physicists with 50 authors and giant projects which people make short, small contributions to. But unfortunately, I think that's just inevitable. If you want to take your measurements to the next level, then you're starting to move beyond the point where one person can make a measurement and write exciting papers every month. There'll always be a place for smaller optical and radio telescopes too.
Thorsten?
With the giant galactic pulsar gravitational wave detector is sensitive to primordial gravitational waves from the epoch of inflation?
Yes, it would be. The problem is that if they're emerging black holes, then that will be a much stronger signal, and it might drown out that primordial signal. But certainly the wavelength range, the frequency range of the gravitational waves is right. The wavelength range you're sensitive to is set by a time baseline. So if you time your pulsars for 10 years, then you can detect a gravitational wave with a period of 10 years. So, so the answer, I think those very long those are the sort of wavelengths that are in the inflation regime. But what I mainly hear from the pulsar people is that Planck and future CMB experiments are the instruments of choice to probe inflationary gravitational waves. But the pulsar timing could provide useful backup to that. But the main goal here is to detect the stochastic background of emerging supermassive black holes.
Yeah, given all the pre-SKA things which are coming online, will they already discovered what SKA is designed to do?
No. Some of the key science projects for these telescopes look very similar to the SKA, but they're all scaled down in size. The most ambitious of all these is ASCAP, and its collecting area is only 1% of the SK mix. So while you can try and do the same things, you can't really compete with the full SKA. One of the very important roles that these telescopes will play is in helping us understand the requirements of the SK science a bit better. So for example, if you want to measure the matter power spectrum of the universe, you can't interpret this data unless you know what the underlying galaxy mass function is. And even locally, we just don't know that well enough yet because so much of the mass is in very low mass galaxies. So one of the things you want to do with ASCAP is do a local shallow survey of every galaxy out to a certain distance. So you had a complete, very accurate measurement of the mass function of galaxies that you could then apply to a more ambitious dark energy project. Similarly with magnetism, if we want to measure nanogauss fields from the intergalactic medium, then we really have to be able to remove the galactic foreground very accurately. And one of the projects that ASCAP will do beautifully is it will give us a spectacular 100,000 rotation measure template of the magnetic field of the Milky Way. That will be, for people like you and me, incredibly interesting in its own right, but for the future it will be crucial in building up a model that we can use to remove the galactic foreground.
So, Earth-like planets are not really supposed to dig deep holes in their disks, like the picture you showed. You need a fairly massive planet to do that. So, I was wondering how...
Well, you don't need a complete gap like this. Any sort of perturbation in the disk should be, I mean, we'll have very high sensitivity and very good ability to see low contrast features. So any disturbance of the disk at all. The point is that you just, if you can't resolve 1 AU from the start, then you don't have anything to say. Another important point about the SKA is that another aspect of planet formation, I believe, I'm not an expert in this area, but my understanding is that in the idea of aggregation from dust to small pebbles to boulders to planets, there's this intermediate regime where the kinetic energies involved are such that the pebbles should not be able to stick together to make bigger things. We don't understand how that happens. The size of the particles at that point is such that they will radiate in the wavelength regime of the SKA. So even forgetting any imaging, just looking at spectra, we'll be able to understand the distribution of particles at that size and how they evolve with the SKA in a way that we simply won't be able to do with ALMA because it's only sensitive to smaller particles. Good.
Maybe I don't worry about the SK capability, but I think that we can also have, for proper interpretation of radio data, some compatible data from other wavelengths. So the question is if in the time the SK is operating, you have the compatible telescopes with 10 milli-arc-second resolution in X-ray and UV up to microwave wavelengths?
Yes, that's a good question. Not every experiment the SK will do is about 20 milli-arc-second resolution. Experiments like the epoch of reionization actually require very coarse resolutions of many arc lengths. You actually want to concentrate as many of your dishes as you can into a small area. But to answer your question, so the SK is one of the pillars of 21st century astronomy, the others being things like the ELTs, in whatever form they will take, X-ray telescopes like Generation X, and ALMA. So when you look in our science, part of our science case is about complementarity and how the capabilities and the timelines for SKA will tie in with all these future experiments. And there's a very nice synergy. For example, in detecting the first black holes, you need the SKA to see the radio emission from these black holes. But then to measure their redshifts, you would need constellation X and X-rays. So there are some things which only the SKA can do, like Faraday rotation and pulsars and gravity. But things like finding black holes or understanding dark energy, you need to complement this with things like constellation X and JWST and so on. So there is very much a partnership between this instrument and the other big telescopes that are being built to answer other questions.
Anwar.
Right, with this, as with any other interferometer, there is a problem with missing spacing, where the telescope has such high resolution, but loses information about large-scale signal. With such huge field of view, it would be a shame to lose the signal at large scales, right?
So I don't think that's, I mean, that's obviously a serious concern for any radio telescope. Let me just show you the animation again while I'm speaking. There's not a real, I mean, that is an issue, but and you're always going to lose something at the very largest scales, unless you have a single dish, and we hope you will have that. But if you look, one of the advantages of having a very small dishes is that you can put them very close together, which means that you have a, I'll bet you it's going to be working. You can put them very close together, which means you have sensitivity of very good, very large spatial scales. And by having small dishes, you also get a large field of view. So what's more, with focal plane arrays, you can increase the field of view even more. So there will always be a limit to the largest scale you can map, and you have to go to heroic efforts to do better than that. But the largest scale that we'll be able to map with the SKA will be certainly much bigger than the largest scales we can map now with the VLA. And a lot of that is driven by the epoch of reionization, because that needs, I don't know why this isn't working, sorry, but that epoch of reionization, the clumps that we'll see of the evaporating hydrogen of the universe will be on scales of several arc lengths. So you really want to concentrate as much of your collecting area as you can into the core, and only very sparsely put collecting area on long baselines. So just to show you a hypothetical distribution of collecting area, I won't say whether this is in Australia or South Africa, but you can see that here's Bilardi here. You can see that all of the collecting area, that's 50% is within 5 kilometres, 75% is within 50, and about 90% within 100 kilometres, and then only a few very limited stations on these long baselines. So I actually see the SK far more as a concentrated collecting area, concentration of collecting area with long baselines as sort of an add-on. It's not a push to higher resolution in the same way that the VLA is. So much of the science depends on centrally concentrated dishes. So I think that good surface brightness will be one of the real strengths of this instrument.
Oh, and class?
The SK will obviously be a very nice instrument when it comes to transient sources, but one problem with some of these sources like GLPs and supernovas and things like that is that many of these are suffering from synchronous absorption at low frequencies. And so they really need a very high sensitivity in that case, and it might not even be possible. Would you like to comment on that?
Yeah, so I actually don't think synchrotron self-absorption is the problem. It is a problem, but it's not the problem. Scattering is the problem. Because if you had a burst like this is at 1.4 gigahertz. If you tried to observe this with, say, LOFAR at 100 megahertz, that would be smeared out over many hours, and it would be below your sensitivity level, as well as perhaps being absorbed, depending on the physics. So yes, I think at low frequencies, finding distant transients is going to be a challenge. But scattering drops as the fourth power of frequency. So certainly the scattering problem goes away very rapidly. And remarkably with this object, if you look carefully, you can actually see that it's a different width at the top than at the bottom. You can actually see scattering just across this narrow band. Synchrotron self-absorption is a whole other story, but that's something that the time domain helps you with. Sources do become optically thin as a function of time, so...
but that might be quite late.
We don't know. But the other thing, of course, is that because the telescope will have such a rapid response, we can also trigger at other wavebands. If you tell me there's been a gamma ray burst, then the beauty of dispersion is I've got perhaps 30 minutes or an hour before the radio waves get to me. So we can be quite flexible, both in terms of we can be very flexible in terms of how we make the measurement. We have time to think about what frequency we want to observe at before the pulse even arrives. And what's more, you always win big there just by accumulating more examples. You might be unlucky with one source, but if you have got this incredible field of view, you're eventually going to accumulate enough sources to get a picture. But you will be able to observe at multiple different frequencies simultaneously between so many megahertz to 25 gigahertz. You won't have to rotate the receiver or have someone go up there and change anything. So if you've just told me that you've detected a gravity wave or some gamma ray event at some position, and 100 megahertz I don't see anything, I can instantly switch up to some higher frequency and watch the spectrum open up as it turns on.
Can we discover pulsars beyond our galaxy in the sky?
You can. We already know of about 20 or 30 pulsars in the Magellanic Clouds, and that number will be pushed up to probably 1,000 pulsars in the Magellanic Clouds. We'll probably have the sensitivity, if you wanted to detect about perhaps 10 pulsars in nearby galaxies. I guess M31 is not going to be an option because it's in the Northern Hemisphere, but whatever the nearest southern spiral is, we'll be able to detect 5 or 10 pulsars. What's really exciting, though, is that the Crab pulsar and a few other pulsars give off these what we call giant pulses. It's not a steady train of pulsars, but every now and then they just give off one spectacular burst. And I forget the exact number, but I believe the brightest temperature of these Crab giant pulses is about 10 to the 45 Kelvin. They're the brightest pulses in the universe. And they're so luminous that if you put the Crab in the Virgo supercluster, we could detect pulses from it with the SKA. So the hope in distant galaxies is not to see a steady train of pulses, but just to see one giant burst occasionally. And if you do this to enough pulsars, and you measure their dispersions and their Faraday rotations, you could actually map out the structure of the local intergalactic medium. And that would be, obviously, an incredibly exciting experiment.
Okay. If there are no further questions, then it's time to thank not only Brian, but also the audience for coming up with so many good questions. Thank you to all of you.